So I started recording. Yeah, so let me just repeat the part that I said before starting the recording. In this session, we're going to mostly talk about this paper, which is considering the problem of reachability in programs. And in a wider context, what we're going to do in program verification and what this course is about is basically that we have some program and some property, and we want to somehow prove mathematically that our program has this property. Or if the property is undesirable, we want to prove mathematically that our program does not have this property. Now, we've seen many different ways of proving stuff. For example, we've seen Hoare logic. And in Hoare logic, we had these triples of the form that I'm writing in the chat. So we had triples of the form PCQ, which basically meant that if the precondition P holds and we run the program C, then we are guaranteed that the postcondition Q also holds. So this is what we basically call a specification. So we say this is how we are saying we're formalizing the property that we want to hold. But then we also saw the concept of a proof, right? And a proof in Hoare logic was basically a tree of rules. We were applying rules over and over again and getting new triples until we get to the triple that we wanted. So that's one of the proof concepts that we have seen. But we've also seen other proof concepts for other problems. So we looked into the problem of termination or halting, for example. And there what we did was that we found a proof concept, and the proof concept was basically a ranking function. So a proof concept is nothing but a mathematical structure, something that proves the desired property. So if the desired property is termination, then one proof concept that we can have is a ranking function. And then we went on and we actually talked about the problem of safety. So we have some undesirable state, and we want to make sure that our program never reaches that state. Or maybe we have a set of undesirable states and we want to make sure that our program never reaches them. And for this case, we talked about invariance, and we especially talked about inductive invariance. So for the problem of safety, we had inductive invariance, which were kind of like our proof concept. So in order to prove that our program is safe, that our program does not reach some bad state, what we did was that we could find an inductive invariant and then show that that bad state is not inside our invariant. And because the invariance over-approximated the set of reachable states in our program, we could then say, okay, even this over-approximation does not cover that bad state. So the program would definitely not reach that bad state. So this was the proof concept that we had for safety. Now, if you go back and look at what we were doing with graph games, you see that there are many parallels here. So, for example, termination is basically a very specific type of reachability, right? So termination is this idea that we want to reach the last line of the program or the end point of the program. And if we consider our program as a graph game, well, of course, because our state space is infinite, then this would be an infinite graph game. But then when we're doing termination analysis, we are basically doing reachability analysis or solving for reachability objectives in this huge or infinite graph game. And then safety is just the same. So when we are doing safety analysis on our program, we can also think of the states of the program as the states of an, again, infinite two-player graph game. And then we can say that what we're doing is that we're finding strategies for safety. And I'm talking about strategies here because, of course, our programs can have non-determinism in them. But what's really interesting is what happens if we want to do general reachability. So we've seen termination already, which is a very special type of reachability. It's just reaching the last label or the end of the program. But what happens if we want to do just normal reachability? First of all, what are the use cases? So suppose that you have a program and you want to somehow show that this program is correct, right? And let's say that correctness is basically safety. So you are given a program and you're given a set of states that are undesirable, and you want to prove that your program never gets to those undesirable states. We've seen that we should do this, or we can do this using inductive invariance. But how do people do this in real world? So what do programmers do? It's not very often that programmers just write inductive invariance for their code. I mean, of course they should. If they're writing safety critical code and they want to be sure that their code is correct, they should write invariance. But usually that's not how in the real world programmers do their coding, right? In the real world, the way that it works is that we are usually hunting for bugs. So we have a program, we have a set of undesirable states, which are the buggy states or the error states. And what we do is that we repeatedly look for ways of reaching this set. And every time we find a bug, we find a way of reaching an error, we just change our program. And we do this over and over again, right? So there is this famous quote by Dijkstra who says that testing can only show the presence of bugs, but can never show the absence of bugs. And that's correct. But what happens if we are really focused on showing the presence of bugs? So this is the topic of this session. So suppose that I'm given a program and I'm also given a set of undesirable states, and I want to prove that my program is incorrect. I want to prove that my program can reach those undesirable states. So what does a proof for this kind of property look like? Do we have a proof concept for this? Can we have something like a ranking function or something like an inductive invariant that proves the incorrectness of our program? Okay, so this is the general overview of this session. But what I'm going to do right now is that I'm going to start with something a little bit different. So when we were talking about termination, I talked about these three nice properties that we would ideally like our verification algorithms to have. And these were soundness, completeness, and termination, right? So I want my verification algorithm to be sound, complete, and I also want my verification algorithm to terminate. I don't want it to run forever. But let's now look at these concepts from the point of view of proof concepts. So let's say that I have some property P, and let's say that I have some proof concept C for this property P. So a proof concept is basically, as I said, just some mathematical structure that proves the property. So because C is not really a program, it doesn't make sense to talk about termination here, but it makes a lot of sense to talk about soundness and completeness. So when can we say that a proof concept or a proof system is sound, and when can we say that it's complete? So generally speaking, it's very similar to how we did for verification algorithms. So for a given property P, I say that my proof concept is sound if whenever there is a proof, then the property holds. So for example, think about Hoare logic. If you somehow find a proof in Hoare logic for some Hoare triple, then that proof really shows that that Hoare triple holds in the given program, right? So soundness is this idea that whenever a proof exists, the property should hold. And of course, we expect all of our proof concepts to be sound. I mean, it's very weird to have a proof concept that is not sound. That probably isn't useful at all. But what's completeness? Completeness is, well, the opposite, right? So whenever the program has my property, I want to be sure that a proof exists. And completeness is usually the tricky part. Because you have to somehow be able to say that if this property holds, if the program satisfies this property, then I have a proof. And there is really no restriction on that proof, except that it should be in your proof concept or proof system. And actually, it's well known that Hoare logic is also complete, but I'm not going to talk about that. I'm going to talk about the simpler proof concepts that we already saw. So let's talk about the case where our property is termination and our proof concept is a ranking function. For this, we've already seen that we have both soundness and completeness. So we've already seen that if I have a program that terminates, then I have a ranking function. This is completeness. And we've already seen that if I have a ranking function, then my program terminates. This is soundness. Okay? And we've seen proofs of that, of both soundness and completeness. But we didn't see this for inductive invariance. So let's say that my problem is safety. So I have some program, I have a bunch of states, and these states are undesirable, and I want to prove that my program never gets to these states. And let's say that my proof concept is inductive invariance. So the way that I want to prove that I never get to these bad states is by finding an inductive invariant that does not intersect these bad states. Okay, so do I have soundness and completeness here? So let's start with soundness. Of course I have soundness, right? Because basically, going back, an inductive invariant was an over-approximation of the set of states that I can reach. And if I find an inductive invariant that does not intersect my undesirable states, then I know that my program also never reaches those undesirable states because the inductive invariant was an over-approximation. And so, yeah, having an inductive invariant is proof enough and it's sound for safety. But do we have completeness here? So in other words, if I give you a program and if I give you a set of undesirable states, and if those undesirable states are not reachable in that program, can you always come up with an inductive invariant? Can you always come up with an inductive invariant that does not intersect those undesirable states, basically? So any ideas? Maybe let's do a vote. So who thinks inductive invariants are complete? So say yes if you think inductive invariants are a complete proof concept for safety. Okay. Say no if you think they're not complete. I'm not getting anything. Okay, so we have one no with a question mark. Yeah, actually, our intuition tells us that they shouldn't be complete, right? Because we've seen examples of invariants that were not inductive, right? But actually, inductive invariants are complete. And this is because we have a very special inductive invariant. And that special inductive invariant is basically the set of all reachable states in the program. So if my invariant I at some line, for example, line 2, is basically only the set of states that are reachable at line 2. And let's say that my invariant is the same thing for every line. So at every line, my invariant is just the set of states that are reachable at that line. So I'm not over approximating the reachable states, I'm just getting the exact set. This is actually an inductive invariant, right? Because if you are in a reachable state at some line and you take one transition, you can only get into other reachable states. And because we have this specific inductive invariant, this specific inductive invariant always gives us completeness. But the point here is that we have completeness only if we look into arbitrary inductive invariants. If we say that our inductive invariants should be linear or they should be polynomial or any other restriction, then this doesn't hold really. Okay. So we saw proof concepts, we saw soundness, completeness, and we know that all the proof concepts that we've seen until this point are both sound and complete. But now let's consider the problem of reachability, which is the main problem we want to consider here. And this problem is basically the dual of safety. So the idea is that in the input, I'm given some program, let's call it P, and also a set of states. So let's call this set of states T, because I want to use kind of the same notation as we used in our games sessions. So I have a program P and I have a set T of states. And the question is there a run of P that reaches T? So it's just reachability. Okay. So what are we going to do? We're going to try to solve this in the same manner that we solve termination and also safety. So the idea is that, well, step one is somehow come up with a proof concept. So we have to somehow come up with something that has the same role that ranking functions had for termination, but now for reachability. And then the next steps are very similar to what we did for termination and safety. So the idea is that look at proof concepts of special formats. So for example, linear or polynomial or exponential or whatever. And then find synthesis algorithms for these special cases. So this is the general outline of what we're going to do. Okay. So actually coming up with a proof concept doesn't seem to be too hard for reachability, right? So if I have a program and a set of states, and I want to prove that this program reaches this set of states, so there is a run of P that reaches T, what can serve as a proof concept? Well, the run itself is a proof concept, right? What I can do is that I can actually give you a run of my program. And if this run reaches the set T, then it proves that the set T is reachable. So yeah, this seems like a trivial choice. And it's of course a correct choice, and it's sound and complete. But there is a problem with it. And the problem is that the run can be quite long. So let me show you an example here. Okay. So consider this program. So we have a lot of nested for loops. and our target T is only reached at the last iteration of every loop. And here you can just assume that M is a very large number. So let's say that M is, for example, 10 to the power of 9. Okay. So if I have a program like this, and my question is whether I will ever get to this print statement, then the answer is yes. And of course, I can give a path as a proof that I can get here. But the length of that path is going to be 1, 2, 3, 4, 5. Yeah, it's going to be order M to the power of 5. And that's too bad. So these are the things that, suppose that instead of just printing something, there was a bug that happened here. So these are what we call deep bugs. So these are bugs that can only be found using a really long execution trace of the program. So because this bug is so deep, we can't really use the run that gets to this bug as a proof concept. We have to somehow find other proof concepts. Okay. So I'm going to actually talk a little bit about something called incorrectness logic, but I'm not going to get into it in any detail because I'm going to cover a completely different proof concept here. But I think incorrectness logic is really worth a mention here. So if you consider Hoare logic, it has triples of this form. And what this basically means is that if you start at a state that satisfies P and you run the program C, you will end up at a state that satisfies the condition Q, the property Q. Okay? So this is basically called a correctness logic because what it can be used for is proving correctness. It's like what we were doing with inductive invariance. So in other words, what it means is that, let me say something like this. Let's say that for all valuations that satisfy P, so if I run C on these valuations, then I will satisfy Q. Okay. Now, what happens if instead of having a universal quantifier here, we go with an existential quantifier? And also, what happens if we kind of look backwards? So what I want to define is a completely new triple, and this is sometimes called a reverse Hoare triple. Sometimes it's called an incompleteness triple, and it's of this form. So we still have kind of something that is like a precondition P and something that is like a postcondition Q. But what I want to say is this. I want to say that for all valuations that satisfy Q, there is some valuation that satisfies P such that when I run the program on that valuation, I get this valuation. So the idea is that Q is actually under approximating the set of states that can be reached if we start at P and run the program C. Right? In a normal Hoare triple, the way it worked was that we started at a program P, we started at a state that satisfied P, and we ran the program C, and then Q was an over approximation of the set of states that could be reached. Now what I'm doing is saying, what happens if Q is an under approximation? So whenever I have something in Q, I know that there was something in P, some valuation in P, such that if I ran C starting from that valuation, I would get to this valuation in Q. Okay. So if we have something like this, then of course it can be used for reachability, right? Because I can start at my initial state, whatever invariant that I have at the beginning of my program, and then I can just see if I can ever reach T, which is the set of buggy states, the set of states that I want to prove I can reach. So by changing the definition of the Hoare triples, we can actually get a completely new logic, and this is usually called incorrectness logic or reverse Hoare logic that has triples that can actually help us prove reachability. Of course, we have to write the rules in this logic. We have to have rules for consequence. We have to have rules for sequential composition, for while, for if, so on. And these actually exist, and they are much different from what you're used to in Hoare's logic. But then if we have such a logic, then we can look into the proof concepts in this logic. We can basically say that our proof concept is proofs in this new logic. Okay. But that's not exactly what I'm going to do. So what I'm going to do right now is that I'm just going to give you a completely different proof concept. And the proof concept that we're going to look into is actually kind of a mixture of an inductive invariant and a ranking function. So we're going to put together the things that we saw in the previous 2-3 lectures and find a new proof concept, this time for reachability. Okay. So let's see. Let's go back to the way that we solved games with reachability objectives, and let's see what we did there. So when I had a game, a 2-player graph game, and I wanted to compute reachability there, I had this iterative algorithm. And the idea of the iterative algorithm was that, okay, I have the set T, and I know that from T, of course, I can reach itself. That's trivial. But then I tried to find all the states from which I could reach T in one step, right? So these were all the player 1 states that had an edge to T, or all the player 2 states that had all of their edges going into T. So these were the set of states that could reach T in one step. And then I added this to the winning set for player 1. And then I continued, okay, let's find all the states from which we can reach T in 2 steps. Let's find all the states where we can reach T in 3 steps, and so on. And this was the idea that we had in our algorithm for reachability in games. Now, what happens if we bring this same idea to programs? So what I want to do is that I basically want to have a new set, and I call this set T diamond, because, well, diamond is kind of like reachability in the linear temporal logic. So we're going to use that notation here. And this set T diamond is basically like the winning set of player 1 in our games. But how can I prove that this set is like the winning set of player 1? Well, what was the conditions that we had in the winning set of player 1? Well, first of all, if we were in this set, then player 1 had a way of ensuring that we remain in this set until we reach our target T. And secondly, because we are now in an infinite system, we have to also be able to show that we will reach t in finitely many steps. And reaching something in finitely many steps is just like termination. So we can also have a ranking function that proves that we can finally reach our states. So let's actually go ahead and formalize all these ideas. So just like the previous session, let's say that we have a finite set of program variables and we call them V. And evaluation is basically just a function that assigns every variable a real value. And again, we model our programs as transition systems. So a program or a transition system is just a tuple. We have a set of variables. We have a set of locations or lines in our program. We have some initial location L0, which is where the program starts. We have a precondition or a set of initial valuations that we can have. And we also have a set of transitions, which is theta. And every transition is basically of this form. So it starts at line L, goes to line L prime, and then does two things basically. So it can have a condition and it can also have an update function. So we can go from L to L prime only if the condition phi holds. And when we go from L to L prime, we apply the update function mu and update the values of our variables. So this is our notation. Okay. And as an example, let me put this here. So if we have this program, so this is our precondition. The precondition just says that every variable is non-negative. And then we have a while loop. And inside the while loop, we have a non-deterministic choice. So at every iteration of the while loop, we either run line B or we run line C. And what line B does is that it increases x by 1 and it increases y by 2. And what C does is that it basically increases x by z and increases y by z, but then decreases z by 1. So we can model this, of course, as a transition system. And here's the transition system right below the program. And the transition system has 5 transitions in this case. And as you can see, some transitions have a condition. So we can go from A to D. Well, this is when the while condition does not hold. So we can go from A to D if X is less than Y. And some transitions have updates. So I can go, for example, from B to A, I can run B and then go back to do another iteration of the while loop. But then I will update the value of my variables when I do this. And generally speaking, a transition can have both, but in the real world, each transition will usually have only one of them. Okay. So these are our transition systems. And we can, of course, now define the notion of states easily based on this. So a state is just a valuation and a line number. So a state is a pair that consists of a line number and a valuation, or a location and a valuation. And just as before, we showed the set of all states by sigma. Okay. And then we can also think of our program as an infinite graph where we have these states and then we have edges between states which correspond to the runs of our program, to the transitions of our program. So we can define the notion of successors. So a state sigma prime is a successor of some other state sigma if there is a transition that takes us basically from sigma to sigma prime. So if there is a transition theta that starts at the line of sigma and goes to the line of sigma prime, which is L prime, And also the valuation at sigma satisfies the condition of the transition, so we can take this transition. And also the valuation at sigma prime, which is nu prime, is the result of this update function of the transition applied to the valuation at sigma. So basically, it's just saying that if you start at sigma, there is a way of executing only one step of the program so that you get to sigma prime. So this is the notion of successor. Okay. And then based on this, of course, I can define runs of my program. And a run is basically just an infinite sequence of states and transitions, such that each state is the successor of the previous state using the transition that is put between them. Okay. So these are all very standard. You know what non-determinism is and so on. And now the problem that we are talking about is reachability, or what's called existential reachability. So let's say that I have a set T of target states, and this is a subset of my set of states. I say that this set T is existentially reachable or just reachable if there is a pass or there is a run R such that it reaches T. So there is a run R and some index N such that the nth state that is seen in that run is in T. And of course, in the definition of run, we have this idea that the run should start at the initial location and it should satisfy the initial precondition as well. Okay. So our problem is problem of existential reachability. I will come back to the other type of reachability later. So the question is, given a program and a set T, can you reach T? Is there a run of the program that eventually reaches T? And you can see some examples of this in the paper. Now, the main notion that we're going to use is, again, the idea of inductive sets. So we want to start with something that looks like inductive invariance and then kind of massage it so that it can prove reachability for us. So I define something called T inductive sets. So given the set T of target states, a set T diamond is called T inductive if it satisfies this condition. And the condition is actually quite subtle and at the same time really easy. So if you take some state in T diamond, some state sigma in T diamond, it should either be in T, or if it's not in T, then there should exist a successor sigma prime such that sigma prime is in the same set T diamond. Okay, so what is the intuition behind this? The intuition is exactly the same as what we've seen for the case of games. So consider the winning set of player one in a reachability game. And just think of T diamond or this T inductive set as the winning set of player one. What conditions do we have? When we are in the winning set of player one, what it means is that either we are at the target already, or if we are not at the target, then player one has a way of making sure that we stay in the same winning set until we get to the target, right? And this is the exact same thing here. So we have a target T. Of course, we don't have the players and the game here. We're directly working with the program. But we have a target set T that we want to reach. And so we define a set T diamond and say that it's T inductive. If for every state sigma in T diamond, either sigma is in T, or if sigma is not in T, if sigma is in T diamond minus T, then there is a successor of sigma called sigma prime in this case, which is also in T diamond. So in other words, if I'm at a state of my program that is in T diamond, I have either already reached my target and proved that the program is incorrect. I can reach a buggy state in T. Or if not, I can take one step in a way that makes sure that I still remain in T diamond. So T diamond is inductive in the sense that I can show by an induction that I will always either remain in T diamond or reach to the target. Okay? Yeah, and this is basically what it says here. So we actually have an example of a T inductive set in this program. So if you consider this program again, I can define a T inductive set for this set T. So let's say that I have my program. Let me actually copy this program into the chat so that we can all see it at the same time. So this is the program. Okay. So let's say that our set T consists of all the states that are at line D and have a value of less than 0 for x. So basically, I want to reach the end of the program. I want to reach line D such that my x is negative. Okay. Now I can have this T diamond, which is defined by these inequalities. So what does this mean? I'm saying that at line A, I want to consider all the states where x, y, and z are less than or equal to 0. And also I have x minus y times x minus y plus 1 equal to 0. Okay. At line B, I want to consider all the states that satisfy these properties. At line C, I want to consider all the states that satisfy these properties. Now, what does it mean when I say this set is T inductive? What it means is that if I look at every transition that I have, so for example, I have a transition here from line A to line D. And this transition can only happen if x is less than y, right? So I want to say that if I'm at a state in A that satisfies these conditions, and if I take that transition, then I will get to a state in D that satisfies this condition. Okay? So, in other words, what I'm doing is that I'm finding an under approximation. I'm under approximating the set of reachable states. Sorry, not the set of reachable states. I'm under approximating the set of states that can reach my target. So my target is to reach D with x less than 0. But what I'm saying here is that if you're at line A and you satisfy these conditions, then you can reach D with x less than 0. If you're at line B and you satisfy these conditions, then you can do this, and so on. But this is not yet quite the case. Why? Because, well, let's go back to the definition of our T inductive sets. What does this definition say? The definition says that at every step, either you reach your target set T or you remain in T diamond. But the problem is that I actually want to reach the target set T. And the definition of a T inductive set does not really get rid of the bad case where I just remain in T diamond forever and never reach T, right? So I have to somehow make sure that I am forced to reach T, and I can't just cycle around in T diamond forever. And okay, this is why I would need something that is pretty much like a ranking function. We call it a T ranking function. So let's say that I have my set of target states T, and let's say that I have an inductive set T diamond. So a function f is a ranking function if it does the following. If it maps every state in this T diamond to some non-negative real value, and also at every transition, I want the value of f to decrease. But not exactly at every transition. So think about this again as a two-player game, but think about it as a two-player graph game where we have infinitely many states. So at every point in time, player one wants to be able to take a step that brings him a little bit closer to reaching T, right? But it doesn't mean that every step should bring him closer. It's just that he should have some choice that brings him closer to reaching T. And this is exactly what we are modeling here again. So I should have a function f that maps every state in my inductive set T diamond to a real number. But it's not exactly a ranking function. The condition that it should satisfy is as follows. It's that if I have a state sigma, and if this state sigma is in T diamond but not in T, then there should exist, so this is existential, there should exist at least one successor such that if I go to that successor, the value of my function decreases by some epsilon. Okay? So again, the idea is very simple. The idea is that this function is actually also giving me a strategy for creating my run of the program. So as long as I am in T diamond, I can always either reach T or choose my next state, my successor, in a way that the value of f decreases by at least epsilon. So the value of f does not always decrease by at least epsilon when you go to a successor. The only condition here is that there is at least one successor such that I can go there and the value of f decreases by at least epsilon. Now, if I have this, what does that mean? That means that if I start anywhere in T diamond, I can always choose that successor that decreases the value of f by epsilon. And this is my strategy. I always choose the right successor. Now, why does this prove that I will eventually reach T? Because, well, f maps all the states into non-negative real values. So the value of f cannot decrease by epsilon infinitely many times. I can decrease it only finitely many times. And when I cannot decrease it anymore, I have to reach T. So because as long as I haven't reached T, there is always a successor that decreases it further. So basically, this is the idea behind what we call an inductive reachability witness. And an inductive reachability witness is our proof concept for reachability. So again, this is just rehashing all the theory. Given a set T of target states in a program or a transition system S, an inductive reachability witness has basically these parts. So first of all, we have a T inductive set, which we call T diamond. And this is the set that we want to ensure our program remains in. Then there is some parameter epsilon, which is the amount of decrease. We have a T ranking function, which means that at every step, we have a choice that decreases the value of f by at least epsilon. And now, if we have these things, these three things, then this is enough to prove that if we start at T diamond, we will eventually reach T. But that's not exactly what we do, right? We don't start at T diamond. We actually start at the initial label L0, and we have some precondition I. So we have to also make sure that T diamond intersects our initial states, because otherwise we can't really reach anywhere. So this is the fourth condition. There should be some valuation nu, such that if we start our program at line 0 and with this valuation nu, then this initial state is in our inductive set, and also this initial state satisfies our precondition. So an inductive reachability witness is basically all of these things. Okay. Now, we're going to use the inductive reachability witness as our proof concept for proving reachability. But before actually continuing with this, let's talk about soundness and completeness and a lot of other stuff. So soundness is again trivial, and this whole informal ideas that I was telling you about is basically proof of soundness. If you have an inductive reachability witness, you have reachability. But why do we have completeness? So why is it the case that if the set T is reachable, then I definitely have an inductive reachability witness for it? Actually, proof of completeness is not so hard, and it's just kind of a mixture of the proof of completeness for ranking functions in case of termination and for inductive invariance in case of safety. So let's do it actually right now. So let's say that I have some transition system S, and I have some target set T. And let's say that T is existentially reachable in S. Okay. What does this mean? By definition, this means that there exists a run in S. Let's call that run maybe R, and some index n such that the n state in the run R is actually in the set T. Okay. Based on this, we want to create an inductive reachability witness. Okay, so what I do here is that I say, let's just use the set of states that are visited in this run as my T diamond. So my inductive set, actually I only need the first n. So my inductive set is just R1, R2 to Rn. And let's say that my epsilon is 1. And let's say the function f just maps Ri to n minus I. Okay. So what I'm saying is that I'm just saying there is a run that reaches T in, let's say, n steps. Just take the states that are visited by this run and call them T diamond. And to each state, just assign the number of steps that are remaining until reaching T and call that F. And this would be an inductive reachability witness. So inductive reachability witness is actually complete as a proof concept. So we have soundness and completeness. In other words, because we have both soundness and completeness, this means that proving reachability is equivalent to finding an inductive reachability witness. The set is reachable if and only if it has an inductive reachability witness. Okay, but why is this useful? So in the worst case, it's no better than just finding a path that reaches T, right? Because that was actually my proof of completeness. My proof of completeness was that I can just take a path that reaches my set T and just work with it a little bit and find an inductive reachability witness out of it. But the main idea here is that, well, inductive reachability witnesses can actually be much more compact. So you can have cases where the shortest path that reaches some state in T is actually quite long. So you cannot actually create the path, but you can have a very compact and short inductive reachability witness for it. And actually, the example that comes to mind is exactly this example that I showed you. So this program. So if you consider this program, it's actually quite hard to just enumerate the path, right? Because the path has m to the power of 5 lengths. But what's much easier is to just find an inductive reachability witness. So in order to find an inductive reachability witness, you should just do two things, basically. You should find an inductive set. And in this case, you can just use the set of all reachable states because you can easily compute the set of all reachable states as your inductive set. And then you also need a ranking function showing that you will get to the target. And again, in this case, the ranking function can just be the number of iterations remaining from the last loop plus m times the number of iterations remaining from the previous loop plus m squared times the number of iterations of this loop, and so on. Okay? So it's actually quite easy to come up with an inductive reachability witness here. And the inductive reachability witness is short in terms of the number of bits that you need to show it. Whereas the shortest path that actually reaches these targets is quite long. So that's the idea behind how we prove reachability. Okay. Now, I'm going to also talk about another type of reachability, which is called universal reachability. And the difference between existential and universal reachability is pretty much down to non-determinism. So what's non-determinism? Non-determinism is, again, this idea that you can have some state that has more than one successor. So when you get to this state, you, of course, have choices of where to go. And in existential reachability, the idea was that there should exist some way of making these choices so that you reach your target T. In universal reachability, the idea is that no matter how you make these choices, you should be forced to visit T. So in universal reachability, the idea is that a set T is universally reachable if starting at some initial value, there is some integer n such that no matter how you resolve the non-determinism, you will reach T, you will visit T in the first n steps of your run. And that's basically the definition of universal reachability. Now, this is, of course, much stronger than just existential reachability. But let me show you how we can adapt all these ideas that we had for existential in the case of universal reachability. So let me find it in the paper. Okay. So again, the intuition here is that we again have a two-player game, and our goal is reachability. But previously, the non-determinism was solved by player one. Now the non-determinism is solved by player two. So when we have universal reachability, the idea is that there is some adversary, someone else, who's choosing what happens when we get to non-determinism. And we want to make sure that no matter how they choose, after n steps, we will reach this target set T. So in a way, it's like a reachability game, except that all vertices belong to player 2 now. All vertices where we have non-deterministic choice belong to player 2. Okay? So this is how we define the universal version of T inductive sets. So we again have our set T diamond, and it's called universally T inductive if for every state that is in T diamond but has not yet reached the target, and for every successor of this state, we have that successor in T diamond as well. So previously, the idea was that if you are at a state in T diamond, you have either already reached your target, or you have some way of going to some successor that still remains in T diamond. Now the idea is that either you have reached your target, or no matter what you do, you stay in T diamond. So every successor is in T diamond. That's the only difference here in the universal T inductive sets. And then for your ranking function, you will also need a very similar idea. So previously, the idea was that if you are in T diamond, you have a way of choosing your successor such that the value of this ranking function decreases by epsilon and you still remain in T diamond. But now the idea is that if you're in T diamond, no matter what you do, the value of this ranking function at your successor will be less than the current value by at least epsilon. So the definition of a ranking function is now that it's a function f that maps every state in your T diamond to a non-negative real number. And for every state sigma that is in T diamond but not in T, and every successor sigma prime of sigma, we know that the value of f at the successor is less than or equal to the current value of f minus epsilon. And then we, of course, have the idea of universal inductive reachability witnesses, which is just the same thing as before. So you should have a universal T inductive set, some parameter epsilon for the decrease of your ranking function, a universal ranking function, and then, of course, again, we have this condition that you should have some initial value that is that satisfies your precondition and is also in your set T diamond. Okay. So now we have these ideas for how we can actually prove reachability, both in the existential case and in the universal case. Now we can do the next steps that I talked about. So just like the case with termination or with inductive invariance, the next step is, okay, this problem that we have right now, this reachability problem, is definitely undecidable because, well, we have basically a Rice's theorem, which says that every semantic property of programs is undecidable, and reachability, be it existential or universal, is definitely one of these non-trivial semantic properties. So we know that if we are given a program and asked, does this program have an inductive reachability witness for a given set of target states, or does it have a universal inductive reachability witness for a set of target states, then these are undecidable problems. But the question, again, becomes nice when we look into special cases. So just like the case of termination, where we looked into linear ranking functions, or we looked into polynomial ranking functions, here we can also do the same thing. What happens if we look into linear inductive reachability witnesses or polynomial inductive reachability witnesses? So what happens if this set, T diamond, is basically only defined by linear inequalities or by polynomial inequalities? Or in other words, what happens if it's a polyhedron or a semi-algebraic set? And also, we can assume that this function f is linear or polynomial, just like the previous cases. And we can actually get synthesis algorithms that are kind of similar. So you can use Farkas lemma, you can use the Handelman's theorem and positive Stellensatz, just like the previous cases that we've seen. The mathematics gets a lot more complicated actually in the synthesis algorithm. So I'm not going to get into that, into how we do the synthesis. The ideas are similar, but you will have to do some more math there. But in general, what I can show you is the final experimental results of how these things work. So here are some benchmarks from the verification competition SVComp. And again, what do we get from looking at, let's say, linear or polynomial witnesses? What we get is exactly the same thing as the case of invariance and the case of ranking functions. We get completeness. So basically, the idea is that the notion of witnesses, of inductive reachability witnesses, is sound and complete for proving reachability. So we cannot have a sound and complete algorithm for synthesizing these witnesses because that's against undecidability. But what we can do is that we can have sound and complete algorithms for synthesizing linear witnesses, or sound and complete algorithms for synthesizing polynomial or exponential witnesses. And that's what we've done here. And then on a large set of benchmarks from this SVComp competition, we actually compared this approach with other approaches. And generally, we see the same trade-off that we saw for the case of inductive invariance. So there are many cases where other approaches are much faster, but then we have completeness. So we can actually handle all of these benchmarks, whereas other approaches cannot handle many of them. So sometimes they just fail and say no answer. Sometimes they time out even after several days of running. So this is the whole idea of why we need these kinds of witnesses. And what's actually interesting here is that when you use this notion of inductive reachability witnesses, your witness is pretty much decoupled from the depth of the bug. So you can have a very short witness that actually finds a very deep bug, a bug that can only be reached after very many steps of execution. And this is in complete contrast to every previous method, like symbolic execution or stuff like that, that actually depend on the length of the bug. And this is something that you would see here. So our runtimes are not really dependent on the depths. Even when the bugs are very shallow, you see that our runtimes are sometimes high. And even when the bugs are very deep, you see that we have quite short runtimes. So that's the whole contribution of using inductive reachability witnesses. Okay, and this was all for today. If you have any questions, please ask them after I stop the recording. And if not, you can leave. So thanks so much. And from